So in the first video, we looked at y is equal to 2 to the power of x and exponential functions. Now we're going to look at when y is equal to 3 to the power of x. This is also known as a tripling function. And doubling is your 2 to the power of x. So let's give x some values here. 1, 2, 3, and 4 should be enough. This will give me some values for y, which is 3 to the power of x. Well, we'll put 0 in too. We'll put 0 in down the bottom. Just to start with, 3 to the power of 0 is equal to 1. 3 to the power 1 is 3, 3 to the power 2 is 9, 3 to the power 3 is 27, it's tripling, 81. So now, what will they ask you to draw? They might ask you to draw this in a range 0 to 4. If they did, you'd have to have a value of 81 on your graph, so you might have to go up in tens. So I'm just going to go up to 3 here because the shape of it's going to be the same. We start at 0, 1. I have to go up to 27, so I'm going to go up in 3s here. 3, 6, 9, 12, 15, 18, 21, 24, 27. So we have 0, 1, which is on all of these exponential graphs. If they don't have a constant in front of them, 0, 1, so it's down low here. And we can go 1, we can make it a bit wider here. 3 boxes, 1, 2, 3, we can fit in here because we're only going out to 3. So 1 is equal to 3, 2 is equal to 9, and a really big jump tripling all the way up to 27 for 3. So you can see again, it's the same shape. This is my tripling graph. Y is equal to 3 to the power of x. And because 3 to the power of x grows so quickly, we never really get that many questions on it that would revolve around real life situations. So let's have a look at a couple of questions that do revolve around real life situations that would come up in an exam. So this is question 9 from your book, page 212. Population of bacteria has a growth model given by the function f of x is equal to 2 to the power of x. They can call this 2 to the power of t or 2 to the power of n as well, where x is the number of days. On day 1, there are 2 bacteria on the Petri dish. So that's your 2 to the power of 1 is equal to 2. What will the population be on day 6? 2 to the power of 6, just use your calculator, is equal to 64. 64 for part B. For part A. Using suitable scales and axes, and this is what they will tell you, draw a graph to represent the population of the bacteria over a week-long period. So we need to fit in 7 here. So you can see my scale is not going to work because 2 to the power of 6 is 64. 2 to the power of 7 is 128. So we need to go up to 128 on the y-axis. So if you count your boxes, 1, 2, 3, 4, 5, 6, 7, 8, 9. There's 10 boxes on this graph. And if we go up in tens, we'd only get to 100. So, but we could probably go up in tens and just put 3 more on at the top. So let's do that. If your graph's not big enough, just make it bigger. So we're going to have 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, 110, 120, 130. Okay, so use your graph to estimate the population on day 4 when we know the answer. Always get the answer. 2 to the power of 4 is 16. We get this one exactly now if we're going to estimate it. So let's look at just growing the graph over a week-long period. 2 to the power of 1 is 2. 2 to the power of 0 is equal to 1. So it's going to be down here. We're doing a week long, so better just do 1, 2, 3, 4, 5, 6, 7. Day 7. And day 0. We were told about day 1 there were 2 in the dish. So we don't know about day 0, but we can see that it is going to be 1. So there's my 2. 2 to the power of 3. Might as well write them down. 2 to the power of 3 is 8. 2 to the power of 4 we have 2 to the power of 5, 32. And we have 6 and 7. So 2 to the power of 2 is equal to 4. We're still below the 10. We're still just climbing up really gradually. 2 to the power of 3 is equal to 8. Just put to the 3 and the 9. 2 to the power 3 is equal to 8. We're still not above the 10, you can see. I'm just going to do a bigger dot so you can see the path of them. 2 to the power of 4 now is equal to 16. 2 to the power of 5 is equal to 32. Just above 32 to the power of 6 is 64. And 2 to the power of 7 is 128. You can see why there's definitely a limit to what they can ask you within these questions just based on how quickly they climb. So a week-long period for 2 to the power of x would probably be the maximum period that they would allow here. And from your graph, estimate the population on day 4. So we go and do a drop down from day 4, drop down from here, and we go across and we estimate day 4 to be this point. Y is equal to 16. Straightforward enough. And then from your graph, estimate the nearest day for the time taken for the population to reach 70. So we're just doing it in reverse now. We're going to the 70, we're going across, and we're going down. You can see 64 was day 6, so it's just going to be slightly after day 6. Now, if you want to get the exact answer, 2 to the power of x is equal to 70. If we get the log of both sides, x times the log of 2 is equal to the log of 70. So this is going forward. So x is equal to the log of 70 divided by the log of 2. This will give you the exact answer, which is equal to 6.129 or 6.13 days. So if you know the answer, that makes it easier to estimate. So we're going down here and we're saying this guy here is approximately 6.13 days. Don't take a risk in saying 6.12 if you know the exact answer. Just say it. So there's another question here. Exponential functions introducing 3 to the power of x. This one is 2 to the power of x. We'll look at another question in the next video from your book that deals in real life situations, and you'll begin to see a pattern emerging within these questions.